You hit it? Okay, good. I'll begin with a word of prayer. Dear Father, we thank you for today. I thank you for these students. Just pray that you'd just help Dr. Wing with his grading and help us to enjoy this lecture, help us to understand what we need to understand about manifolds, and help us not to get too lost in the details, Lord. In your name I pray. Amen. Okay, so I am going 5 minutes over today. I mean, that is settled at this point, right? I mean, okay. So I want to talk to you guys about manifolds. And I want to take a semi-rigorous approach, not quite rigorous, really. And the thing which I'm mostly lacking in terms of careful presentation is the topological aspects of this, right? Carefully speaking, to put a manifold in the right context, we should talk about the topological structure thereof, and I'm completely glossing over that for the most part, all right? But Michael agrees, okay, good. Basically, here's the deal. A manifold is an abstract set, M, which allows calculus, or you could say supports calculus. In other words, a good slogan for a manifold is it's simply some place where you can do calculus in the natural way. And so, turns out, more or less, what that means is that if you look at this manifold M, you have what are called coordinate charts. All right, so you have coordinate charts, and so there's coordinate charts which cover the manifold, say U1, and well, let's say U, and and so the coordinate chart is a mapping from U, it's a bijection, let's say. Well, I could say my notation in my chapter is like psi inverse, but I might call it X. And it's a mapping down here to some kind of open set down in Rn, all right? So, and there's this sets on the manifold, and they cover the whole manifold. And the other thing that makes it interesting is they sometimes overlap. So maybe you've got U tilde, it's another domain. Now this X is called a coordinate chart. Now we've thought about the opposite direction, right? If you reverse that arrow and you go from Rn up to an abstract set, that's what we would call a parameterization, right? Or a patch. So the chart is an inverse of a patch, all right? We have less experience with those in our previous mathematical work. And then but anyway, here's the deal. So you have another chart, let's say X tilde. Well, I'll call it Y. So another chart Y. Then the deal is, if there's some kind of overlap, right? If there's some kind of overlap region, then that's where you get the structure of the manifold, all right? In particular, we're looking at smooth manifolds, all right? And to say it's smooth means that if you look at the local coordinate representative, I mean the overlap chart here, so some people call it transition function. Let's see here, how would you say go from here to here? What map would do that? And of course, I'm talking about on the appropriate, like, the image of the intersection down here. So from that point over to there, what would the mapping be? What's that? Y composed with X inverse. I think I like that. So in other words, X inverse goes like that, right? I take this point down here, let's say U maps up here to P equals to X of U, right? And then back down over here to, X inverse of U. Then you go down over here to Y of X inverse of U, right? And then so that hits some subset of the domain, the range of the Y map, the Y coordinate map over here, all right? The point is, if it's a smooth manifold, a smooth manifold, all that really entitles us to is that it's some kind of topological space. There are these open sets, well, these sets U and U tilde, which cover the whole space. And on any place where they enter, and these sets come paired with bijections to Rn, all right? And anytime you look at a transition function like this, then that has to be a smooth map in the sense of advanced calculus. So y composed with x inverse is basically a smooth map from Rn to Rn. And the smoothness, what does it mean for that to be smooth? It means that you can calculate the Jacobian of that, right? And it's full of smooth partial derivatives, right? So we just say smooth because we want to be able to take as many partial derivatives as we like. And that's a manifold. So, of course, then, well, you said, I claimed that a manifold is a set in which you can do calculus. First order business, then, is, if you've got, say, a function. So suppose here's my manifold, and I've got a function, f, right? And it's a real valued function, so the function maps over here to the real line. How would we differentiate, say, that function with respect to the chart on a manifold? First order of business. So here's a u, right? And so the coordinate chart is x. That gives us down a copy of Rn, right? How would we define partial f, partial x at some point P up here? So manifold theorists can't be trusted. All they do is steal things, all right? But it's okay. They steal things from their friend. Their friend is advanced calculus. So it's always theft from the calculus we already know on Rn. Basically, the question is, how can you define a derivative up here in terms of things you already know? We want to look at a mapping that goes like this, basically, right? So that mapping is what? F composed with x inverse, right? And so the definition of partial f, partial x with respect to a coordinate chart on the manifold is simply, and so down here, let's say we have coordinates u1, u2, un, all right? These are the Cartesian coordinate, all right? The Cartesian coordinate functions, the usual Cartesian coordinate functions on Rn. So this is actually defined to be, so this actually doesn't make sense yet. That doesn't make sense quite yet. I don't define partial f, partial x. I define partial f, partial, the thing I haven't gotten into yet here because it hasn't been required of us yet is that x is actually equal to x1, x2, xn. So there are n component, the chart is this ensemble of n component functions. Each one of these x upper i's is a mapping from u to r. So I should really calculate partial f, partial x, say x sub I, like that. All right? Now that is by definition then simply the following. It's partial ui of what? Of this thing. So of f composed with x inverse of u1, un. Right. And you evaluate that where? X of p, right. Why does that have to be? It's because the thing we're evaluating is it's a function from Rn to R, right? So I have to evaluate the corresponding point in Rn. And that's how you do it. Right? That's the definition. I know that seems pretty abstract, right? But once you get into this, basically we just do everything like we usually do. And if you didn't know this definition, you could still do calculus on a manifold pretty successfully. let me show you an example of that before so I'm gonna use a projector here in a minute, and I'll show you how the properties of this follow from this definition. We'll get some product rule, all the usual bells and whistles. But just as an example, if I had a manifold M with coordinate chart, say x1, x2, x3, and I had f equal to let's say x1 squared plus the exponential of x2 plus x3, right? I could write that. What is it, Joe? Just okay. And then if you were to calculate partial f, partial x1, what would you get? 2x1. See, Joe, you can do manifold theory. Partial f, partial x2, what would that be? What's that? More steps you want to do? So there's no x2 dependence here, and the exponential's derivative is exponential. So we get exponential of x2 plus x3, but the derivative of the inside function is 1 again, so there you go. But, just to be a little bit more explicit, let me just look at an example for a second. What's a kind of oh, my money. Let's see here. So let me just tell you a couple of coordinate charts that are, I don't want to get bogged down with, I'm not sure I ever really want to work an example out with this definition in here. That's not exactly the point of this course. Another example, let's see, how about if you have a unit circle, right? S1, the unit circle, what's a coordinate chart on this? How about theta? So if you take a point P on the unit circle, and suppose that point is, say, x comma y, then what's theta of P? It's, if this is equal to cosine theta naught comma sine theta naught, right, then this is exactly just theta naught, right? That's an example of a coordinate chart. So, or another example, I could have the sphere, right? And I could say, use the coordinate chart, say phi comma theta, with the obvious meaning, right? So it would map over here to, phi theta space. Geometrically, that's easy to understand, right? The actual formulas for it are kind of daunting. Just like up here, I didn't actually write the formula for it, did I? I was kind of sketchy here, right? If I was on the right part, I could use inverse tangent of the quotient of the y over the x, right? But generally speaking, it's the difficulty of finding the standard angle, right? But anyway, that's and likewise here, to actually give you a formula for what the coordinate chart acting on a point on the sphere is kind of messy, right? But geometrically, you understand what that is. That's a coordinate chart, right, on the sphere. So, if I was to tell you, some function of theta or phi and theta in this one, then you could differentiate it in view of that definition. But, all right, let me go on. So the other, I will get back to the properties here, but I have a little bit more to do before I do that. The other important definition that we want to talk about is What does it mean for if you have two manifolds, right? What if you have two manifolds? Say m and n. And what if you've got a function going from m to n? Right? What does it mean for that function to be smooth? How do you judge whether this function's smooth or not? Well, what you do is you look at a coordinate chart x for m, and you look at, say, at the point P, all right? And over here, you're looking at the point f of P, right? So suppose that close to f of P, there's a coordinate chart y for n. These don't have to be the same dimension. So say m is an m-dimensional manifold, and n is a n-dimensional manifold, right? Then in order to say that this is a smooth function, what you need is that the local coordinate representative of f are smooth in the sense of advanced calculus, in the sense that they have a Jacobian, right, which would be an n by m matrix here, right? So what's the mapping that we need the smoothness of in order to have smoothness of the function on the manifold? So y composed with f composed with x inverse, right? I need that is a smooth in the sense that the Jacobian of that mapping, right, has smooth partials, right? I mean, that's a convenient, anyway, characterization of it. As we learned, that was equivalent to assuming the real differentiability, assuming that we have continuity of the derivatives, right? So smoothness of a function from manifold to manifold is judged by the smoothness of the local coordinate representatives. Now, you have to have that's true for all possible representatives. So if there's more than one chart it takes to cover the manifold, then you have to check each different possible overlapping chart selection. Okay, so hey, I got an example here. You could think of this as being m. You could think of this as being n, right? And so I can define f of theta, right? I could say f of theta is equal to, let's say, theta squared 3 theta. That would be, I could understand that as a mapping from the circle to the sphere. That's not quite right. Let me see if I got that right. Well, yeah, I'm going to back off that for the moment. I don't want to get into that at the moment, actually. All right, so let me go through the proof of some of these properties with you. Come on. All right, I hope it works today. What do you think the odds are? Ooh, come on. Please work. So guys, I'm trying to, I'm mostly using my notes as the guide today. I think if you read Rentland, it's excellent and really complementary to my notes. If you put those two together, I think you've got a pretty good slice of what's going on. Okay, so yeah, I actually have some examples here, and I show you, a manifold with several charts, and I look at the overlap of the charts and show that they're smooth, to show, in fact, that you have the smoothness of the overlapping charts is that makes them compatible charts if they're smooth like that. For example, this one. Here's the unit circle, And instead of using the theta map, which is just geometrically easy, you could also use just like project onto the x-axis or project onto the y-axis. So you could take the right map for the right half of the circle, left half of the circle, map onto the y-axis, take the right half of the circle, map onto the y-axis, top to the x-axis, bottom to the x-axis, and these projection maps, they overlap on quarter circles, right? And then you can check that the overlap, the transition functions on those quarter circles is smooth. Like for example, if I look at the overlap of the right map and the top map, the composite of the coordinate chart with the inverse of the upper map, the inverse. All right, so it's like to get from the point x back to the point it projected from, you go from x to the square root of 1 minus x squared, right? That's the corresponding point on the circle that map that projected down to x. And then the right map, what does it do? It just projects out. It projects out the y component. And so that gives you this. And the question is, well, is that a smooth map? Well, that's not a smooth map when x is plus or minus 1, right? But those are exactly the points that are outside the consideration on the overlap. So, and you can do similar calculations to show that the overlap of the other coordinate charts on each quarter circle are smooth. And so that defines what's called an atlas on the circle, right? An atlas is like a system of maps that covers the whole space, right? And they have to be made consistently. This is an old problem, right? We've been trying to put maps on things for a long time. For example, the trouble of putting a map on the Earth is well known, right? You can't find a map which doesn't distort part of the Earth, right? If you try to map all of the Earth at once onto a flat thing, you have trouble, right? You're going to mess up something somewhere. And the problem gets worse if you look at more exotic spaces. You really do need more than one map even just to cover the whole thing. It's worse than just distorting. Sometimes you just need multiple maps to cover the whole thing. And that's where this definition of a manifold comes from, ultimately. All right, I digress. Let's try not to do this. So here's the, stop that. Here's what I was just drawing on the board. Smoothness of a function from one manifold to another. Really, the definition I gave you for the smoothness of a function is a special case of that in some sense. You can also talk about a curve, right? What would a curve on a manifold be like? It would be a mapping from the reals, right, to the manifold. You got some curve, right? How do you judge whether that's a smooth curve or not? Well, you look at its local coordinate representatives, which would be like this. So that's kind of opposite to the differentiability of the function I was just looking at, right? You're like, well, wait a minute. Why aren't you also having? Why isn't this down here? Why don't you have another mapping the coordinate chart on the reals? What do we take the coordinate chart on the reals to be by default? The identity map, right? So in fact, that's our default. That's our default, right? In Rn, we'll just use the identity map as our go-to coordinate chart. It's a global coordinate chart. It covers the whole thing. It's a bijection, right? Now, you could put other coordinate charts on Rn, right? You've done that in calculus, right? On R2, you can use xy coordinates, right? But you could also use polar coordinates. And some of our more interesting problems will be putting non-standard coordinates just on Rn. That's one of our happy places to experiment. So, what's another example of a manifold before I get back to the properties? How about linear algebra? Think about a vector space, right? In a vector space, if you pick a basis, what's the coordinate chart? It's a mapping from this abstract set of vector space to Rn, right? It's a bijection. If you take two different charts on a vector space, right? They're kind of, this picture is kind of unnecessary, right? Because the coordinate charts on a vector space are global because the basis spans the whole space, right? So if you look at coordinate charts on a vector space, that usage of the term chart is consistent with this. What are the overlap functions? Well, it overlaps on the whole vector space, and if you take two different coordinate charts, they're related by what? By an invertible linear transformation, right? If you change basis, it's just multiplication by an invertible matrix. Is that a smooth mapping? It is in fact smooth, yes. So vector spaces are sometimes called linear manifolds for this reason. All right. Oops. Sorry. So this was the definition I gave you guys just a second ago. Here's the properties of partial differentiation with respect to a manifold. Let me make that bigger. Manifold chart. The derivative of a sum is the sum of the derivatives. You can pull constants out. You've got the Leibniz rule, right? You've got, if you take the partial derivative of one component of the coordinate chart to another, you get the Kronecker delta. Do you look familiar? They should look familiar. My point is, when you do differentiation with respect to the chart on a manifold, it's just like ordinary calculus that you already know. You even have a chain rule. If you have two coordinate systems at a particular point, they're related. If you take partial f partial yj, it's the same as taking partial x partial yj times partial f partial xk summed over k. In other words, this is the chain rule relating two coordinate systems, right? But there's something more to see here, right? And I was just foreshadowing comment. What happens if you pull off the f? Like just strip off the f. What do you see here? You have partial yj. Sum k equals 1 to m of partial x partial k, partial yj, partial xk. Maybe if I wrote it with bars, it'd be even clearer. So I have like partial x bar is equal to partial x bar, partial x summed over. You should recognize that's how the basis for a vector transformed. That's the transformation law for a basis of a vector space. Which suggests maybe we can use partial xj as a basis for a vector space. That vector space is going to be called the tangent space. All right, but I'm jumping ahead here. I just wanted to look at these just for a minute. I don't want to write them out. For example, how would you, prove the addition law? Well, you just go back. You differentiate on Rn the corresponding representative, and then because the composition behaves with addition like that, right? I mean, the sum of a composite, right? This is just that again because of the way composition works. And so you get that. And this one's maybe more interesting. If I take xi composed with x inverse, well, if you study this, if you think through this, this is exactly the u sub I map. So what's partial u sub I, partial u sub j? Well, that's Kronecker delta ij for the reasons we talked about earlier in this course. And every one of these proofs, it boils back down to once you get past the abstraction, the theft of pulling it back to Rn, it's always just the usual Rn thing that proves it. Like here's the proof of the chain rule. Partial f partial yj would be. I need to use the w's are the component the Cartesian coordinates down on the image of the y chart. And so I do the composite of f composed of y inverse of w. Now I want to convert this to, I'm going to change it to things in terms of the x chart. So what I do is I compose with x and x inverse, common trick, right? And compose with identity. That makes sense where they overlap. And then using properties of composites of maps, I have this is composed with that. But x composed with y inverse of w is actually u1 of w, um of w. And then I've got an ordinary differentiation of a composite function down on Rn, and I can use the ordinary chain rule. So by the calc 3 chain rule, if you will, I do the partial derivative of the kth component of this, x composed with, okay, right. With respect to uk, now what's in the kth spot is this mapping, which remember was x composed with y inverse. right? So this then is the derivative of the inside function. Then we're taking the sum over the derivatives of f composed with x inverse over each one of these, right? So there it is. I mean, that's the multivariate chain rule. And then I just convert back. This is nothing more than partial x, partial yj. And this is nothing more than partial f, partial xk. And there you have the chain rule for manifold coordinates. All right. Sorry, I'm going to put this away. All right, so we have, at this point, described how you measure whether...
Technology blocked.
Yeah, okay, yeah. Nah. That's okay. I needed a rest. All right. So, I have hopefully at least described for you briefly what a manifold is. There are more examples in my notes and also in Rutland. This is I described to you how we measure whether a function's smooth, right, from the manifold to the reals. Also, how you determine whether a function from one manifold to another is a smooth function. The next chapter in this story, of course, is the tangent space, right? How do we define tangent vectors to a manifold? And I've already kind of hinted at that. It's going to have something to do with derivatives, but I need to make a definition. A derivation on the smooth functions, let's say, at the point P on a manifold M is, let's say, x, which goes from the smooth functions at P and M to the reals, and which is what? Linear and Leibniz. So in other words, x of f plus cg is equal to x of f plus cx of g. Right, that's for all f and g smooth functions at P. When I say a smooth function at P, I mean a function which is at least smooth relative to some locality of P. All right, and it could be more technical. You could say it's a germ of functions or something. We're actually working on equivalence classes of functions or something, but whatever. Now, and also Leibniz. So that means, bless you, that if we take the product of f and g, then that's actually going to give me x of f times g plus f times x of g. So that's the Leibniz property, or the basically it's a product rule, right? And so basically the proposition is simply this. I mean, there's obvious, remark, I guess, like proposition, remark, I don't know what you want to call it. Partial xi at the point P is an element of the derivations at P on M. Oh, so let's just say that such an x is an element of the derivations at P of M. Just to give a name to the set of all derivations. Yeah, I probably should use it on whenever I'm taking a function as an argument, I sometimes use brackets, but it's not sacrosanct or anything. I usually use, I don't know, you can go either way. It's not terribly significant. So certainly a partial derivative is a derivation, right? But here's the interesting thing. On a smooth manifold, that's kind of all there is. This is a much harder result theorem. If x is an element of the derivations at P of m, then x is equal to, it works out to, it happens to be the case, sum I equals 1 to m of x upper I partial x of I at P. So not only are partial derivatives derivations, in fact, any derivation at the point P can be built with partial derivatives in this simple way. In other words, the so-called coordinate derivations, so we say partial xi is a coordinate derivation. You can see that the coordinate derivations at P, in fact, provide a basis. So what this theorem also happens to say is that if we look at the derivations at P to m, that's the span in the usual real sense, partial x1 at P to the partial xn at P. Yeah?
In that second to last thing with the summation, what are you taking the partial with respect to xi of?
Nothing.
Nothing?
The derivation's an operator. It's an operator equation.
So it would be
How
whatever-
dare you, sir?
I have to print something.
You have to print something.
It's not my fault.
Are you coming back?
I don't like this class.
Are you coming back?
No, I don't like computer science.
You don't like this? I'm getting very confused. You don't like this class?
I don't like computer science 111, and I have to go print something for computer science.
Oh, okay. All right.
So if I had my choice, I would be sitting here listening to you talk about manifolds, but I have to go print this.
All right.
So I'm not happy about it.
That makes me feel better.
Okay.
I'm glad you're not happy about
I
it.
just realized the derivation function looks like dirt, and now I can't get it.
Oh, no. It's dirt.
Oh, well, if that, so derpum, I will fix that for you. We will soon say that this is the tangent space to P at M. So we're going to say that the tangent space to a manifold is simply the set of derivations at the point. This is one viewpoint. There are several other viewpoints for what the tangent space to a manifold is. You could say that the tangent space, well, I mean, what's kind of the most geometric definition of a, if you're thinking about, here's my manifold, right? I take a point P, right? What would you think is the tangent space at P to a manifold? I mean, we did it before. We did what? Just look at all possible curves, right? So you might look at like curves and say, well, the tangent vectors to curves, right? Those are vectors at P. That's kind of what we did earlier in Rn, right? And in fact, well, that doesn't quite do it justice, right? Because if that's the tangent vector to that curve, it's also the tangent vector to like this curve, right? Or this curve. So really, it's you could say tangent vectors are associated to equivalence classes of curves at the point P. But they're also associated to these derivations. I guess the question is what is the isomorphism between these objects? I mean, I describe in the notes there's three different ways of thinking about the tangent space. The one is derivations. The other is just equivalence classes of curves, right? The corresponding vector, the tangent vector to those equivalence classes of curves. And yet another way, which is kind of more physicsy, is that it's a set of objects that transforms contravariantly at the point. Let's see here. What would the let's try to remember. Oh man, all of a sudden, drawing a blank. Sorry, this is what I was trying not to do today. But I got to get it out of my system, otherwise I'm going to... I think I've been careful to rewrite Chapter 10 so I only talk about derivations. I think I'm now trying to violate that new principle I had set forth, so I better stick to my guns and just talk about derivations, but if you want to, I can explain to you how this is in fact isomorphic to, say, looking at equivalence classes of curves. And I think if you look at previous editions of my advanced calculus notes, you'll find explicit isomorphisms. When I took a course in manifold theory, we spent like a week proving that the space of derivations is interchangeable with the equivalence classes of curves, is interchangeable with the set of objects which transform contravariantly. There's different viewpoints of the tangent space. All right, so let me be more explicit here. Before we talked about a tangent vector looking like what? It was something like p comma, what was it, v1, v2, vn, right? That would be maybe a tangent vector to some if M was a subset, if M was a manifold, as we discussed it before, embedded inside Rn, and so this would be something in what? This might have been an element of the tangent space to P at M, right? That's what we looked like. That's what, before we got to this part of the course. We certainly were not thinking of them as derivations, right? So how do you trade this object for the corresponding derivation? It's simply this. You do x is the sum, I equals 1 to n, of v upper I partial x I at p. I mean, I suppose partial ui would be more appropriate since that was before on Rn, right? But yeah. That's basically all it is we're using the partial xi as like a basis for the tangent space. Okay. Probably be helpful. Oh, so to give you something more specific, well, okay, so that's the tangent space at a point is just the set of the derivations at that point. This theorem is non-trivial, by the way, to prove that every derivation can be written as just the span of the coordinate in terms of a sum of coordinate derivations. That actually requires the smoothness of the manifold, and it's kind of like a theorem of Carr-Theodori result in here that's a little bit technical and not in my notes. So that's not entirely easy to prove. In fact, this fails to be true if you looked at a manifold which is, say, type CK, where k is less than infinity. So yeah, suppose you had only like third derivatives of your transition functions. It's actually no longer the case that you can look at the tangent space as derivations, because the set of derivations becomes infinite dimensional. Anyway, what happens if you, instead of, say, just one point, suppose you give me a tangent vector at each point on the manifold. What's that called? If you apply a particular vector at each point on the manifold, it would be a vector field on the manifold, right? So if I free up the point, right, and I just look at, say, partial xi would be what? This would be a vector field, right? Be a vector field where it would be a vector field on the domain of the chart. Okay. Like if you go back to my examples here on the circle, if I fix a point, there's really just kind of I mean, of course, we can draw the tangent space like that, like the ancient Greeks, right? If we fix that point, you've just got partial theta at that point P. That's, I mean, up to a scalar multiple, that's what it is. And so there's just one vector field on the circle. It's just basically this. On the sphere, you have two vector fields that are interesting. I mean, you got partial phi and partial theta. Those are your vector fields on the sphere. Not the whole sphere, though, right? Up to the coordinate defect. Like, that's not a global chart because we lose a point because we don't have injectivity all the way around. We have to have that angle jump somewhere. And so if I the tangent space to the sphere is two-dimensional, right? Okay. What else did we do with mappings before? We did what? We took the derivative of mappings from one set to another also, right? Now, I told you how to take the partial derivative of f with respect to a coordinate chart, but what I have not yet described is sort of the analog of the differential, the Fréchet derivative. So that's what I'll talk about now. And I'll try to do more examples as we go on here. I just got to get everything in front of us here. So this is what's known as the push forward. So suppose I've got some manifold M and some other manifold N, right? I've got some smooth mapping from one to the other, F, right? Then I can look at the tangent space to P at M, which I'll just draw like that for a second, just to kind of give us a picture of it. And it turns out I can take tangent vectors in the tangent space at P and M, and I can push them forward over here to the tangent space to F of P at N. Now, maybe it's wrong to draw the tangent spaces on the same picture. I mean, they're really separate objects. They're spaces of derivations, if you were listening, right? I mean, so there's an abstraction there, right? I'm no longer really thinking of them just as the local approximating planes for the tangent space. I mean, you can fall back on that as a numerical, in the context of the manifold being inside Rn, sure, fine. But, these manifolds could be sets of matrices or something. So, I mean, I don't know how useful thinking of the tangent spaces actually as geometric subsets of the larger space is. I mean, it's still a useful intuition, but these are really abstract things. Okay, so I've got, here I've got some vector, let's say, which is x, a derivation, an element of the tangent space at P to M. And I want to define a mapping called the push forward, like this, which now I am still, oh man, there's something I was gonna notation wise. Now I tend to use this, and I'm still, there's a viewpoint which I haven't entirely adopted, which maybe there's a reason not to use both of these, like I think the viewpoint is this, is that we should, well, I'm gonna use this. So DPF, which you might also denote as the push forward at the point P, all right, is going to be a mapping from the tangent space at P of M to the tangent space at F of P, well, to this. How do you define it? So, all right, so what do these do? These eat smooth functions based near F of P, right? So in other words, I have to explain what is the, I have to take dpf, I let it act on the vector x, right? And I have to tell you how this thing, what does this thing do to the smooth functions over there? That's what I need to do in order to define the tangent vector. All right, so it's going to be x. Now x only acts on, what does x do? X eats smooth functions based at p, right? How do I get a function based at t from what I have here?
What is G? G is,
Let's see here. Yeah, g would be like this. G maps to the reals. It's a real valued function on n.
tangent space on n.
Just from n.
Oh, okay.
Again, I probably should draw the tangent spaces as a separate picture. That'd be better. But it's, I don't know, there's an intuition that's useful to draw them in the same picture. So I want a function that goes from p to the, oh, it's g composed with f. All right, there you go. See, because g composed with f goes, f takes you from p over to f of p up to g. This makes sense. And there you go. That's the definition of the push forward. Joe is underwhelmed. Understandably. This is kind of like just alphabet soup, right? Like, how do you actually calculate with this in coordinates is a more interesting question for those of us who want to do like coordinate-based calculus, right? What does this look like when you pick a system of local coordinates? Well, so in other words, suppose that you have coordinate charts. Suppose we have, x1, x m here, and suppose over here I have, say, y1, yn over here. So coordinate charts x and y. So in order to define this properly, I need to do what? Tell you how it maps a basis to a basis, right? So first of all, dpfx should be an element of the span of what? Partial y1, partial yn. Now, admittedly, those are all at the point what? At f of p. But I'm not, you'll forgive me if I omit the at f of p symbol on every single one of those for the moment. Oh, fine, I'll do it for clarity. You talk me into it. Gosh, I hope you're happy. So that has to be in there, right? But in particular, dpf, dpf did it. So dpfx would be the sum, right? If you accept the theorem that I didn't prove over there, it should be the sum, j equals 1 to n, right? Of what? X of what? X of the y component functions, y upper j, times partial yj at the point f of p. I'm just using the theorem that I didn't prove. But on the other hand, what does x have to look like? It's a sum I equals 1 to m of x of xi, partial xi at p. Which we typically just denote this as x upper I, kind of like we've been doing for tensors and such. So when you put that up in here, what do you get? You get the sum over I equals 1 to m, sum over j equals 1 to n, and I get x upper I And then this partial, I get partial xi of yj. So I get partial yj partial xi partial yj at the point f of p. You're like, well, by conservation of indices, that's what had to happen, right? I mean, you got the I contracting with the I, the j contracting with the j. The net result has no indices, right? It involves the coordinate system at p. It involves the coordinate system at f of p. This almost had to happen. But you could use this as a definition of how you calculate the push forward, right, at a point. Now, again, some people insist on some people would say you take the push forward of a vector field, right? So this is only at one point right now. Now, to get the push forward of a vector field, I just allow the point to vary. I do this at more than one point. And so if the stars align correctly here, we'll take a vector field to a new vector field. But you got to be careful, because if the function you're looking at doubles back on where it started, you might attach 2 points. You might attach 2 vectors at the same point in the range, which would then give you something that had 2 vectors at a point, which would not be a vector field, right? A vector field is an attachment of a vector at one point. Just one, one vector for one point. All right. Let me work an example. Yeah. Now, again, this is a rather fast tour through manifold theory. You really, if you're interested in these things, should take a semester and study a proper book and just dwell on these things, right? There's great books. Tu's manifold theory book or John Lee's manifold theory book, which is great, very, very detailed. I've liked Jeffrey Lee's book for more kind of it's a little bit more computational. But there's so many excellent books on manifold theory. You guys are very fortunate. Okay, so an example might be this. I could look at f going from, say, R2 to, I'll do R2 to R2. It's kind of boring. Or I could quote my son and say, boring. And let's see here. I guess I could just do the usual thing, like f of r theta is equal to r cosine theta, r sine theta, right? So I'm thinking of r theta coordinates here. I'm thinking of x, y coordinates over there. So if I look at the push forward at some point p, I don't really care what the point is, of f of partial r, what happens? So just to reiterate, I'm going from a space with partial r and partial theta as my derivations over to another space where I've got partial x and partial y as the derivations at a point. Right. This is I'm really thinking of the point being fixed here, but okay. So this is what. Do you want me to do? I guess I can go back to I can either use this formulation or I can use that formulation. I think I'm going to do. I guess I'll do this one. If I look at partial r, I'm really looking at x with x1 being 1 and x2, like the big X. Big X number 1 is 1, big X number 2 is